Till now we have discussed the tensors of rank 2. Particularly, you have seen the covariant tensor of rank 2, contravariant tensor of rank 2, and the mixed tensor of rank 2. You have seen actually these tensors are defined by the particular law of transformation. It means when you know the components of these tensors in one of the coordinate systems, then how we can find the components of those tensors in another coordinate system. Today we are going to discuss the tensors of higher rank. So this is nothing different. This is simply the generalization of the transformation laws which you have seen in the case of tensors of rank 2. So here we will simply consider the tensors of higher rank or higher order, particularly the mixed tensors. So first of all, we will see the definition via the transformation law, how these tensors of higher rank will be defined. So for this, let us consider, like previous lectures, a space of n dimension. And in this n-dimensional space, we consider a set of n raised to the power r plus s quantities. And let us say these quantities are a contravariant indices p1, p2, so on pr, and covariant indices q1, q2, so on qs. Actually, these n to the power r plus s quantities are in a coordinate system S, and in this coordinate system S we consider the independent variables are xi, where I is 1, 2, 3, 4 and so on up to n. In fact, these n to the power r plus s quantities are known as the components of a mixed tensor of rank r plus s, where r is the contravariant rank of this tensor and s is its covariant rank. Actually, these quantities will be called the components of the mixed tensor of rank r plus s if they are related to n to the power r plus s quantities in another coordinate system, let us say S prime, in which the independent variables are denoted by the symbol x prime I, where again I runs from 1, 2, 3, so on up to n. But only when these quantities will be transformed in accordance with the particular transformation law, which I am just going to mention here. So let us see how these quantities will be transformed from coordinate system S to S prime. So if you write the components of these quantities in S prime frame by A prime, let us say M1, M2, so on, MR, and covariant indices N1, N2, so on, Ns. You may write here the commas or you may not write the commas. Without comma it is also written. So let us drop writing here the commas. Without commas you can write these things. So I am not writing here commas. And so first of all we will write what? As you have learnt in the previous lecture. So first of all we will write the components of these quantities in the S frame, and those are what? They are A contravariant indices P1, P2, so on PR, and covariant indices Q1, Q2, so on QS. Now remember the laws of transformation of the mixed tensor of second rank and generalize that transformation law. You can easily say what will be the other factors here. You know this will be del x prime m1 over del x p1, del x p1. Similarly, del x prime m2 over del x p2, and so on. Del x prime, you can say mr by del x pr times. Now for the covariant indices we should write here del x q1 over del x prime n1. You can remember del x q2 over del x prime n2, so on. Del x qs over del x prime ns. So this is the transformation law in accordance with which the components of this mixed tensor will change from one coordinate system to another. I hope you have understand, because this is nothing different from the tensor of second rank. This is just a generalization. Now in fact this tensor A, which I have mentioned here, is actually called a tensor of the type RS. So a tensor of the type A, P1, P2, so on, PR, covariant indices Q1, Q2, so on, QS. In fact, this tensor is called a tensor of the type RS, is called a tensor of type RS. It means first of all you should write the contravariant rank of the tensor, then after writing this comma you should write the covariant rank of the tensor. So this tensor is of the type RS. For example, if you consider a tensor, let us say Aij, can you say what will be the type of this tensor? You can easily see that in this case the contravariant rank of this tensor is 2, but there is no covariant indices, so the covariant rank of this tensor Aij is 0. So you can say that this tensor is of the type 2, 0. So this is a tensor of type 2, 0, 2, 0 type tensor. Similarly, if you write this tensor, let us say A covariant Ij. So you can see in this case the contravariant indices are not here, and so the contravariant rank of this tensor will be 0. But there are two covariant indices, so the covariant rank of this tensor is 2, and therefore you can say that this is a tensor of the type 0, 2, 0, 2. So this is 0, 2 type tensor. Remember, this type of tensor will be very significant when we will actually discuss The algebraic operations like the addition of tensor, subtraction of tensor, then this will matter. So remember this thing. If you take another example, let us say Aijk. Here you can see I is the contravariant index and j and k are covariant index. So you can say that this is a tensor of the type 1, 2. 1, 2 type tensor. 1, 2 type tensor. Let us illustrate this idea by a proper example. For this illustration, let us consider a tensor denoted by the symbol Aijk PQRS. You can say this is a tensor of the type what? This will be a tensor of type 3, 4. Here 3 is the contravariant rank of this tensor and 4 is its covariant rank. Now, in accordance with the transformation law, if you want to find the components of these tensors in another coordinate system, then what will be its component? You can easily say. Let us consider that A prime IJK PQRS. These are components of a tensor. Let us say AUVW LMNT in frame S prime. Then what we have learned, on the basis of that you can easily say how this transformation will be carried. You can see that this A prime contravariant indices IJK and covariant indices PQRS, this will be equal to A UVW LMNT. Now write the partial derivatives. You know this will be del x prime I over del x u times del x prime j over del x v del x prime k, you can say, by del x w times del x l over del x prime p. Del x prime p. Again del x m over del x prime q. Del x n over del x prime r and del x t over del x prime s. So in accordance with this transformation law, the components of this tensor will transform. So I hope you have understand how the tensors of higher rank get transformed from one coordinate system to another. Now, after getting the idea of such a transformation law for tensors of higher rank, we will discuss a very important tensor which is actually known as zero tensor. So what is the concept of this zero tensor? We will see now on the basis of this idea. So let us see what is a zero tensor. Zero tensor. Actually, uh, if all the components of a tensor in one coordinate system are 0, then uh, then they are all also 0 in another coordinate system at that given point. And such a tensor is called a zero tensor. In simple way, you can say that a tensor whose all components vanish is called a zero tensor. So in one line you can define it: the tensor whose all components vanish is called a zero tensor. Actually, this zero tensor is very important in constructing the physical laws. So we must know the idea of this zero tensor. As a definition, you say that in case of a zero tensor, all of its components is 0. And one very important theorem regarding this zero tensor is that if all the components of a tensor is 0 in one coordinate system at a given point, then all these components are also 0 at the same point in every coordinate system. This is a very important theorem, and this theorem is actually utilized to construct the physical laws. So this zero tensor is of great physical importance. So first of all, we will prove this statement that if all the components of a tensor in one coordinate system are 0 at a point, then they are all 0 at this point in every coordinate system. First of all, we will prove this. So you can say, if all the components of a tensor in one coordinate system are 0 at a point, then they are all 0 at this point in every coordinate system. So this is actually a very important theorem. And first of all, we will prove this important theorem, and then you will see later on that this very important theorem is very important, or just a basis to construct the physical laws. So for proving this important theorem, let us consider again the components of a tensor in coordinate system S, and their components we will find in another coordinate system, let us say S prime. So let A contravariant P1, P2, so on PR, covariant indices Q1, Q2, so on QS. These are actually the components of A in coordinate system, let us say xi. And again we consider that A prime M1, M2, so on, Mr, N1, N2, so on, Ns. These are actually the components of A in coordinate system, let us say x prime I. Then just you have seen how these components in coordinate system where independent variables are x prime I will be obtained if you know the components of this tensor in coordinate system xi. Then just you have seen. So according to the transformation law, you can say that this A prime M1, M2, so on, Mr, N1, N2, so on, Ns. You know this is equal to A P1, P2, so on, PR, Q1, Q2, so on, Qs. And del x prime M1 by del x P1, so on del x prime Mr by del x PR times del x Q1 by del x prime N1, so on del x Qs by del x prime Ns. You know. Now conversely, if you know the components A prime M1, M2, Mr, N1, N2, Ns, then you can easily find what will be the components A. It means if we know A prime, then we can just find the components A. So conversely, if the components A prime contravariant indices M1, M2, Mr, covariant N1, N2, so on, Ns are given, then the components of the same tensor A contravariant P1, P2, PR, covariant Q1, Q2, Qs in the coordinate system coordinate system xi are related as, you can write just taking the converse of this equation 1, you can write a contravariant p1 p2 so on pr and covariant indices q1 q2 so on qs. This is equal to a prime m1 m2 so on mr n1 n2 so on ns, and just take the reciprocal, or you can say converse of these partial derivatives. So this will be del x p1 by del x prime m1 so on. Again take the converse of this. This will be del x pr by del x prime mr, and here is del x q1 by del x prime n1, you should take its converse. So this will be del x prime n1 by del x q1 so on. Again take the converse of this. This will be del x prime ns by del x qs, and say this is equation 2. Now you can see from this equation 1 and this equation 2, if you consider that the components of this given tensor is 0 in a particular coordinate system, so if a p1 p2 so on pr q1 q2 so on qs is equal to 0, then from equation 1 you can see, if you consider that these components are 0, that is the components of the given tensor in frame S is 0, then from this equation 1 you can easily say that these components a prime in frame S prime are also 0. Then from equation 1 you can say that a prime m1 m2 so on mr and n1 n2 so on ns is equal to 0. And again you can see, if see the equation 2, if you consider that this a prime m1 m2 mr n1 n2 ns are 0, if we consider that if a prime m1 m2 so on mr n1 n2 so on ns is equal to 0, then from equation 2 you can see that this a p1 p2 so on pr q1 q2 so on qs equal to 0. So in accordance with the structure of equation 1 and equation 2, you can easily see that if the components of a tensor vanish in one coordinate system, then they necessarily vanish in all other admissible coordinate system. So the statement which I have mentioned it here, you can see I have mentioned this statement here, that if all the components of a tensor in one coordinate system are 0 at a point, then they are all 0 at this point in every coordinate system. So this statement or this theorem, you can see, has been proved. So hence the theorem is proved. Theorem is proved. And as I have told you earlier, that a tensor whose all components vanish is called a zero tensor. So if a tensor is a zero tensor in one coordinate system, definitely this will be zero tensor in another coordinate system too. So this is a very important theorem, and actually this theorem is very important in the formulation of physical laws, as I have told you earlier. And this is the property which constitutes the importance of tensor in physical laws. So this is all about the tensors of higher rank. And now, after getting the idea of tensors of first rank, tensor of second rank, and in general tensors of higher rank, now we will actually discuss the most important concept in forthcoming lectures, and those are actually the different algebraic operations in tensor algebra. And after that we will see the tensor calculus, but first of all we will discuss tensor algebra.